तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last two lectures on curve representation, we discussed about parametric cubic curves and cubic splines. We also introduced Bezier curves, the Bernstein basis, and we will start from where we left off in the last class and continue with Bezier curves and then move over to surfaces. So, we will have lots of equations and derivations. So, kindly be ready, and of course, a few illustrations will be also accompanying the mathematical expressions for each of these curves representation. So, Bezier curves, we talked about this representation about this that means it must lie within this polygon, starting point, end point, tangents to the curve should be the first and the last edges of the polygon, and the equation of the parametric Bezier curve t running from 0 to 1 is given by this, where this j and I is called the Bezier or Bernstein basis or blending functions or even binomial coefficients. Ith inner order Bernstein basis functions are given by expressions of this form, and we will now see what do these shapes depending upon the value of n and I, that is the order, will be treated by two parameters and the value of t which varies from 0 to 1. We will see how the function looks like and dictates the nature of the curve. Okay, so, these BIs are also called the control points in the previous expression of the Bezier curve which we have seen, and the j and I we will henceforth call them as Bernstein basis or Bernstein blending functions. J and I is the ith nth order Bernstein basis function, and is the degree of the defining Bernstein basis function or the polynomial curve segment, and which is one less than the number of points used in defining the Bezier polygons. So, if you have n plus 1 as the number of points used to define the Bezier number of points used to define the polygon, that means the number of points, if it is n plus 1, then n is the order of the Bernstein basis here. Okay, these are some examples of the BBF or the Bezier Bernstein blending function. If you see here, for n equal to 2, there are 3 possible values j20, j21 and j22, because n is equal to 2 and I could vary from 0 to up to n. So, you have j20, j21, j22. So, this is the first curve j20, this is j21 and j22. Okay. Again hand simulated, but if you generate it using a computer simulation using the expression given in the previous couple of slides back, t varying from 0 to 1, you will get this same. How many curves will you get for n equal to 3? For n equal to 2, you got 3 curves j20, j21, j22. If n is equal to 3, you will get j30, j31, j32 and j33, 4 curves. So, let us look at those, the nature of the 4 curves. Here it is what you get for n equal to 3 cubic Bernstein basis, t again varying from 0 to 1, j30 is the first curve here, j31, j32 and j33. As you can see, it is a symmetrical nature of these curves and the smoothness at the ending point, which lends itself to the curves fitting with respect to the end points and their tangents. Okay. But we will see the boundary conditions of this Bernstein basis first, and see that they have not only good symmetric properties, but good starting and finishing properties in terms of their values and tangents as well. So, come back, this is what will the n equal to 2, the quadratic n equal to 3 cubic Bernstein basis functions will look like. And interesting to note, j30 is this one, is just replicated mirror reflection of j33. Similarly, j31 is a mirror reflection of j32. Here also the same, j20 is a mirror reflection of j22. Let us look at the endpoints. So, here this was the Bernstein Bezier function 0 to 1, and this was the Bernstein basis. J n of I is defined as this. We have noted this down in the previous class, or note this down right now. also the t varying from 0 to 1, the n combination I is given as this particular expression. Let us look at the limits for I is equal to 0 for this particular function, with the constraint that 0 factorial, which we will need, and the 0 factorial and 0 to the power 0 both are equal to 1. So, we put this in mind and look at the limiting condition when I is equal to 0 here. If you look that if you substitute j n of 0 of the t is equal to 0, if you substitute here these conditions where I is 0 as given here, t is also 0, you will get it as 1. Okay. This is what you will get. So, that is interesting to note, that means the n 0 of the 0, the starting point when t is equal to 0 for any order will start at 1. For any order when t is equal to 0, the first curve will start at 1. Okay. If I is not equal to 0, that means for any other non starting curve when I is not equal to 0 means not j n 0, that means j n 1, j n 2 and so on, that this it will start at 0. This is interesting. The first curve starts at 1 and all other curves start at 0. Can we verify this using the previous diagram for the quadratic and cubic case? Let us go back. Yeah, as you can see here, j 2 0 starts at 1, all other curves start at 0. The same thing here, j 3 0 start at 1, all other curves start at 0. Followed the logic? I again repeat, j 2 0 starts at 1, all other curves j 2 1 and j 2 2 for the quadratic case start at 0. Here the cubic case starts at 1, all other curves also start at 0. Good. So, this is what we have derived here. This was as that the j n 0 of 0 for any n, and it could be 2, 3, quadratic, cubic case starts at 1, all other curves when I is not equal to 0, they start at 0. What about the finishing case when t is equal to 1, j n of n, if you substitute back into the expression when I is equal to n, if you substitute here in this expression I is equal to n, you should be able to obtain 1, and j n for all other I not equal to 1, you should get 0. That is also interesting phenomenon. That means, the last curve when I is equal to 1 will finish at 1 and all other curves will finish at 0. You compare this boundary condition when t is equal to 1 with the condition here at the initial condition when t is equal to 0, the starting condition. All curves start at 1 and they finish at the first curve starts at 1, okay, and all other curves start at 0. As far as the finishing condition is concerned, at the ending condition bound when t is equal to 1, all other curves will end at 0, the last curve will finish at 1. Let us go back and check this condition as well. You see here, the last curve j 2 2 finishes at 1, all other curves finish at 0. j 3 3 finishes at 1, all other curves finish at 0. So, this is the interesting symmetrical starting and finishing conditions which you see. The first curve starts at 1, the last curve finishes at 1, the first curve starts at 1, the last curve finishes at 1, all other curves except the first one start at 0, all other curves except the last one finish at 0. The same thing here, all other curves except the first one start at 0, all other curves except the last one, they all finish at 0. Isn't it interesting, the Bernstein nature of the Bernstein basis, which is illustrated using the quadratic and cubic case in this figure, and it is true for any n, 4, 5, whatever you visualize. You must remember, if you remember these two figures or those boundary conditions mathematically, it will be easy for you to visualize the Bernstein basis nature, the smoothness in the, of course, you can look into the derivatives of this expression and find out that some of these curves except the first and the last one will have a peak somewhere. If you look back here, the j 2 1 has a peak at t is equal to 0.5, the j 3 1 and j 3 2 will have peaks at 1/3 and 2/3 respectively. Okay, that is interesting, and all of these curves intersect at 0.5. And there, of course, there are other interesting properties of this Bernstein basis which we will see. I hope you have copied at least these two curves, because whenever we come across new properties in the series of discussions here with Bernstein basis, you should be able to get back to this figure yourself. Okay. It could be difficult for me to roll back, but you should be able to visualize this figure from your notes and see that the properties are satisfied. So, for right now, just remember the starting and the finishing conditions for the first and the last curve. Okay. 1 and 0, okay, and this is also 1 and 0, starting at 1, all others starting at 0, last curve finishes at 1, all others finish at 0. The same thing for the cubic case. So, we will roll forward. We have seen the starting case, we have seen the finishing case. Thus, P of 0, since j n of 0 starts at 1, the first point B of 0, the B naught is the P of 0, the B naught which is the coefficient to be evaluated for the Bernstein is the P naught. So, how do you evaluate the other one using boundary conditions? B n also will be P of 1, because G n of n is equal to 1, we have seen that if you substitute you will get. So, the what you get as the coefficients B naught and B n nothing but the starting and the finishing points. And so, the curve must start at B naught now and finish at B n. We talked of this as one of the conditions in the last class. We talked of this polygon with n points, the curve must start at the first point and finish at the last point. Okay. So, that is what is the mathematical condition here. P of 0 is B of 0, B 0, and P of 1 is B n. Good. So, for any t, this is also another interesting feature. For any t, sum of all the values of all the Bernstein bases for any value of t starting from 0 to 1 is equal to infinity. Look at the normalization nature of the curve. Take an any t, quadratic, cubic, or even higher order. For larger values of n, if you take any value of t, sum of all of them up, you will get a value 1. And I believe this is an exercise for you to find out mathematically, even for the quadratic or cubic case, for any value of t or for any general value of n, that this value is 1. It will be very interesting proof. Try this out. Some points I should leave it as an home exercise. So, this is one of them, okay, for the class today. So, coming back, for any t, this is what you should try to prove or find out. Also verify, this is also interesting proof, where the j n I of t can be represented as j n minus 1 t and n minus 1 I minus 1. That means, the next order curve of the next higher order Bernstein basis can be represented in terms of previous basis of lower order basis of j n minus 1 I and j n minus 1 and I minus 1. That will be very interesting. Okay, so this is something like a decomposition, in the sense that one higher order curve can be broken into two smaller parts, or two lower order curves can be joined together to build a higher order curve. Okay. And of course, I should be more than 1 and all that. This is a boundary condition here, a limit for the case of I, which should be of course less than n, and it should be more than 1. Okay, although I placed in the reverse way, but you can follow here. So, this is what I meant, that if you are talking of n is equal to 3, any particular curve for any arbitrary I can be derived, provided those limits of I are maintained from the quadratic curves, let us say. Two quadratic curves can yield a third degree curve and so on. So, by just simply summation sum of products form, one is a 1 minus t and t factor, which you need to find out. Okay. So, this also verify as a mathematically this proof that this is possible for you to derive. Okay. So, these are the terms which you need to remember to derive these two conditions. For any t, sum of this j n I is equal to 1 and the n of I t, nth ith order Bernstein basis represented in terms of lower order n minus 1 and n minus 1 I minus 1. These two to derive, you will need these formulas, which are the expressions of the Bernstein basis. You know that. Well, I will give you a few examples for the Bernstein basis, these factorial terms and the combinations, where n and I, this factorial, this combination can be written as this. You can use these for to derive what we will say as the J30, J31, J32 and J33. For the cubic Bernstein basis, as you can see, when n is equal to 3, we said that there are 4 curves. For quadratic n is equal to 2, there will be 3 curves, J20, J21, J22, and for a cubic case n equal to 3, there will be J30, J31, J32 and J33. So, these are the expressions. I leave it as an exercise for you. Use these expressions very easily, substitute them, and this is also given very simply as it is here. Simply substitute that, this is what you get. Okay, you see, all of these are cubic polynomials of t, the J30, and the nature of these curves you have already seen. Those two figures which you have seen couple of slides earlier for the quadratic n equal to 2 and the cubic n equal to 3 case, they are nothing but these expressions which you are seeing in the slide right now. Have a look. The first curve which start from 1 and finishes at 0, and all of them, these two also will start at 0 and finish at 0. This curve will start at 0 and finish at 1. That these were the properties which we discussed for the Bernstein basis. I repeat, this first curve starts at 1 when t is equal to 0 and finishes at 0 when t is equal to 1. These two curves for t is equal to 0 and 1, the boundary conditions, will start at 0, end at 0, and this curve for t equal to 0 will start at 0 and wind up at the value 1 when t is equal to 1. Interesting? Good. So, you can rearrange in that form which we discussed a couple of classes earlier or in the previous class as well, where the p of t for a cubic Bernstein basis or Bezier curve of order 3 when you substitute from the previous expression these J3 zeros onto the expression of the Bezier, you will have this that B0, B2, B3, B1, B2 and B3 are the geometric points. We define the polygon, and if you substitute and rearrange, I leave it as exercise for you to write it in terms of T, N and B, T, N and G for n equal to 3. This is what you get as your matrix formulation of the Bezier curve. Okay. Again, this is a third home exercise which I am leaving now. Lots of derivations here. If I do spend time on this, I thought you should practice it yourself to gain confidence. Okay. Simple manipulations, not much difficult. You should still practice and not simply copy them from this slide. I leave it as an exercise for you to try this after the class when you go back. Okay. So, this is what you have as your T, N and B, which you can write from this particular expression of your cubic basis. For n equal to 4, in fact, this is what you keep trying again. It will be t to the power 4 raised, and there should be 5 because one more than the number of points, should be one more than the order of the Bezier curve. So, you have 5 control points for the polygon and B0 to B4, and I leave it you again as an exercise to obtain these matrices as we have done for the cubic case here. Remember, we first derived this. That means we derived, if I go back, we derived first these J3i's, then we wrote the PT and then wrote this expression, correct, T in terms of T, N and G. So, you do that same thing for the n equal to 4 case. That means you derive your J40, J41, J42, J43 and J44, 5 of them. I repeat again, J40, J41, J42, J43 and J44, 5 of these you define, you derive them, obtain them, their nature, then write the expression of P and P of T, and then try to group these terms into different categories and write the expression as given in the matrix form T, N and G, and sometimes it is written as F dot G. G is this geometric constant vector, and this the blending function F could be visualized as a weighted parametric curve in terms of raised to the power 4. Good. So, this is what we have for F, this is what we have for F, where the Ji's are it can be written as a matrix form in terms of these Jni's, Jn0, Jn1 up to Jn. And what are these Jni's? And this these Jni's are nothing but what we have to derive. If it is n equal to 3, then you have J30, J31 up to J33. If n is equal to 4, you would have had J40, J41 up to J44. That is what you would have defined your F. But in terms of T and G, if you look at the T is a very straightforward matrix, it depends upon the order. N equal to 4, it starts from T to the power 4. If n equal to 3, you will have only these 4 terms, T cube to 1, and this matrix N, which is the most interesting matrix, I can define in terms of lambda ij. I have a formulation for this lambda ij to define the elements of this matrix for n equal to 4 or the previous matrix n equal to 3. Here you look at this matrix, in fact, the lower triangular one is almost a null matrix, elements zeros. You can, in fact, you have the upper left triangular elements only. So, that is what we can define in terms of this lambda ij's, and they formalize this. Please note down the lambda ij's. If I plus j is lying within this range 0 to 1, 0 to n, excuse me, then you can use this formula. If I plus j exceeds the value of n, you use the value 0. This will help you to see that these elements are non-zeros in the left upper triangular matrix, in the lower right triangular matrix, either for n equal to 4 or for n equal to 3. As you can see here, the upper left triangular has non-zero values, lower left triangular values has zeros. This is for n equal to 3, for n equal to 4 the same thing happens, upper left triangular non-zero, lower left triangular, and this is formulated with the help of this lambda ij's. Because I plus j, if it lies between 0 to n, you are talking of elements which are lying in the left upper triangular matrix. Very interesting, lower right triangular matrix elements. If you sum up I plus j, the element index to that element of the matrix, that will roll over n, and in that case use a value 0. So, this is the expression which you have for the lambda ij's, and the coefficients of the successive binomial coefficients also can be derived. Okay. I take this as another home exercise, and also I will request you to obtain the expressions for J2i and J4i. Okay. Computation of successive binomial coefficients also can be obtained using this expression. I leave this exercise for you to verify this. This is a very simple, because this formula was given to you earlier. So, just that is very simple and trivial, it should be easy for you, and also I leave it as an exercise to obtain the expression for J2i and J4i. J3i is what we have derived, I leave it as an exercise, the quadratic case and the quadruple case, this is the case of 4, okay? J4i. Good. So, we will move on to a very nice interesting property outside mathematics, which we will see as the recursive geometric definitions of Bezier curves. Recursive geometric definition of Bezier curves. Let us say we take 3 points P0, P1 and P2. We take these 3 points P0, P1 and P2, and if you have 3 points, that means n equal to 3. What should be the order of the Bezier Bernstein basis or polynomials or even the Bezier curve? The order should be n minus 1. So, if n is equal to 3, it should be a second degree. So, second degree curve lying within that polygon, starting from P0 to P2, tangentially should start from P0 to P1, follow that edge first, then go somewhere to the middle within the polygon and end tangentially in the arc P0 to P2. So, again if you look back, it should start at P0 tangentially here, wind up. Of course, you can obtain all using the mathematics, given the coordinates P0, P1, P2 in 2D or 3D, you can obtain the curve, but let us look at the geometric recursive definition, which will be very interesting. That means, can I find the set of points which will lie on the Bezier curve starting from P0 to P2 and controlled by P1. Of course, you can have more number of points, nobody stops you from having more number of points, okay? That is P0, P1, P2, P3 and so on, but it will be interesting to first have a look at this and then of course, extend this philosophy if you have more number of points. Just look at a triangle, this definition is very interesting. We take the bisector point P0 to P1, this label point I say is the bisector, okay? The midpoint between P0 to P1 is marked here. Similarly, I mark a midpoint between P0 to P2, it will be somewhere here. So, that is the midpoint from P0 to P1, the next midpoint from P0 to P2 is here. I join these two midpoints. The first midpoint of P0 to P1 is joined with the next midpoint between P1 to P2, and then I obtain another midpoint of this new line. Midpoint will be somewhere here, which I label as PA. This is the first point I obtain where the curve must pass. The Bezier curve passes through the point PA. It will start at P0, wind up at P2 for value t starting from 0 to 1, T1 to T2, in this case 0 to 1, and it must pass through that point PA within that triangle. This is the definition of the first curve. Now, we can use this definition recursively to look for points to the left of PA and to the right of PA. That means, within the triangle between points between P0 to PA, have a look into this figure. Now, we have to look for points between P0 to PA and points between PA to P2, because we have now guaranteed that if the curve starts from P0, passes through PA and winds up at P2, we have to look for points to the left of PA, which lies between P0 to PA, and then again also between points to the right of PA, which lies between PA and P2. Now, as you got the point PA from the triangle P0, P1, P2. I hope that idea is clear, or should I roll back once again? This was the starting point. That means, you had a triangle P0, P1, P2 and I obtained a point PA. How? I roll it once again for you for a clarification. How do I get this first point PA? Given a triangle P0, P1, P2, my problem is to get PA. I get the first, I get the first midpoint, the left between P0 to P1, get the next midpoint P1 to P2, join these two lines, obtain the midpoint of this line, which is joining the midpoints. That is the method by which I get P. If I could do that to get PA from P0, P1 and P2. I repeat, if I can obtain this PA, remember I have labeled it as a different shade than the other midpoint, because this is a point on the curve. So, this point PA is a point on the curve obtained from the points P0, P1 and P2 a triangle. I can similarly obtain from these 3 points. What are they? P0, then this first bisector and PA. These 3 will form another triangle, another polygon. P0, this point with first midpoint, and PA will form another polygon, and using that I can get another point here through which this curve must pass. Let us do that. I will roll it straight away without in steps. So, from that point I roll forward 2 midpoints, one bisector and then this midpoint again. This is the same of what I did to get P A. Let me roll back one step. I am concentrate on P 0, this first midpoint and P A. I visualize only this part of the triangle and see how can I get this the point here, which is a new point, and this is the recursive part that I am using the same logic of P 0, P 1, P 2 to get P A. As I use this logic here, I am using this, I am calling that function again and passing these points P 0 midpoint here and a P A to get this second point to the left of P A. This is the point which will come, and this new point P B is another point which will be lying between P 0 and P A, and the curve must also pass through that. Recursively I have used that, and I can do it to the right of P A. Between P A to P 2 I can use a similar definition. This triangle if I use, I can get another point. Let us try that. Look at the line bisector joining midpoints and the midpoint again, that is a P C. So, now you see I have got 3 points. First I have a function call from P 0, P 1, P 2 to get P A, then I recursively call the same function and pass P 0 this point and P A, and then P and to the right of it P A second bisector and P 2, and I get, and I can keep doing this again and again. I can generate points between P 0 to P B, P B to P A, P A to P C and P C to P. All of these will start from triangles, and I can recursively keep calling them, and finally I will get a set of points, and then that is what the Bezier curve will look like. This is the Bezier curve. I did mention that this curve will pass through the points, it has to pass through the point, not only it will start from P 0 and wind up at P 2, but it also must pass through P A, P B and P C, and the rest of the points also can be generated using similar function. I hope you have understood this logic, but I will probably roll this back once more. This was the starting point. So, the first method was to get the P A. This is how you get the bisector, and that is what you get. A recursive call from P 0 bisector, first bisector and P A will give me another point P B, good, and another recursive call for the triangle P A second bisector and P 2. The bisector of P 1 and P 2 is this point and P 2. So, this is a triangle, I can get the second point, third point P C, and the curve will pass through these points, and I keep taking these small triangles and keep recursively calling them and keep generating points, and this is what the set of points which I join to get this Bezier curve. This is a very interesting recursive geometric definition of Bezier curves. I hope you like the methodology with very little mathematics in terms of matrix multiplications, cubic, degree, manipulations, permutations, combinations, starting point, end point with burst-in basis. Very interesting phenomena here, how recursively I can keep doing this function of obtaining 2 bisectors of the triangle edges, joining them, get the bisector. This is the main function. I keep recursively calling them as I keep developing new points and generate newer and newer triangles to the left and right of each set of points I generate. Okay. So, this is what look into the point. So, now if you feel here that the curve starts from P 0 and passes through these points P A, P B, P C and has to of course end at P 2, you can see that the overall nature of this curve can be controlled by oscillating. If we keep changing this P 1 position, keeping P 0 and P 2 unaltered, all these points P A, P B, P C and other points of the curves will change, and so these are my control points. I keep changing P 1 and my curve states varying, and I can add a few more points. I can add a few more points, and this has to all follow that particular logic. Okay. So, I leave it an exercise for you to read about what are called the B splines represented as blending functions. Of course, remember we had talked about cubic splines and Bezier curves. I think with the time available to us, we have to move to surfaces. So, I leave it an exercise for you to read about cubic splines using burst-in basis. Splines using burst-in basis, which are called as B splines. Remember, we talked of cubic splines and Bezier curves with burst-in basis. Merge the two, splines with burst-in basis are called the B splines. Very interesting functional forms. Read about B splines, which are also widely and commonly used, represented as blending functions. Also read about conversion from one format to another, and knots control and knot points, how they play an important role, and also the condition when B spline could become a simple Bezier curve. I leave these as an exercise for you to read with the due to time limitations available. to us in this series of lectures. We will move on to surfaces, and this is a trivial example of a sphere which you know the Cartesian coordinate form. ABC is the center of the sphere in 3D, R is the radius, and this is the parametric form. In fact, it is the representation of the sphere or equations of the sphere in polar coordinate form r, theta and phi in 3D. I started with this simple example because the sphere is the most common example in the 3D surface which we used, but before we move on to generic expressions of quadratic surfaces and in fact complex surfaces based on even Bezier, we will go through a few other examples very fast before moving on to generalized expressions and see illustrations as the last part of the coverage of the curves and surfaces representation. So, look back, I hope you are able to copy these expressions. The first one is of course very simple and straightforward. Look into the ranges of theta and phi. This is the equation of the ellipsoid. It has 3 parameters a, b, c, the Cartesian coordinate form on the top and the polar coordinate at the bottom. Again the ranges of theta and phi are given. That is an example of a torus, okay. And the expression is given in both Cartesian coordinate form with respect to r, theta and phi. It is a little bit different than what we had seen in the previous case of a sphere and ellipsoid. This is the example of torus. This is an example of a super ellipsoid where it is an ellipsoid all right, but you have these coefficients S1, S2 which you can vary and give the ellipsoid various types of structures as you feel necessary. So, these were the 3 different forms of expressions of special types of quadratic surfaces. We look into the general expression of a quadratic surface which is an extension of the general conic which we have seen earlier. Remember there were about 6 parameters for a generalized conic which we use boundary conditions to evaluate about a couple of classes back. So, we will look back into the slide and see the general expression of a quadratic surface which has 10 a, b, c, d, e, f, g, h, I, j. So, there are 10 parameters to the generalized expression or a general expression of a quadratic surface, and the above is a generalization of the general conic equation in 3D. In matrix form it takes the shape like this. This we have done for the conic as well in 2D, and in 3D we have a surface a quadratic. So, we have this x and x transpose, and this is the symmetric matrix S. Now, you can insert the factors 2 here. If you remember, we did that with the conic in 2D and take care of this half and 2 terms, these factors in the diagonal and the off diagonal terms differing due to the nature of the symmetric matrix, you need a factor of 2 extra there. So, it is possible that you can avoid a, b, c and k, you can avoid the factor 2 there. You do not need a half factor if you provide the terms of d, f, e, g and h. These are the terms which are contributing to the off diagonal terms symmetric nature of the matrix. If you put a 2 there, this matrix S has a very decent shape without having this factor of half and 2 inside. So, you know this concept from the generalized conic. Now, parametric forms of the quadratic surface are often used in computer graphics. You do not mainly all the time use generalized expressions because they are difficult to handle in math unless you are very keen to handle matrix manipulations. Okay. Parametric forms give a good visualization. So, we will go through again as much as possible different special type of quadratic surfaces and their parametric forms. So, let us look back. Ellipsoid is given here. We had already seen this earlier. We will see into this elliptic cone. Now, if A is equal to B, it is a perfect cone. Elliptic cone will have A is not equal to B. Okay, that is an expression of a cone in parametric form. Hyperbolic paraboloid. Well, we will see this example of these surfaces in the next slide, but just note down these expressions. We have a cosine hyperbolic and a sine hyperbolic terms. Okay, and z is phi square. Okay, hyperbolic paraboloid, very interesting properties. Elliptical paraboloid also as given here. Okay, and then we have the hyperboloid in general given by a product of a cosine and a cosine hyperbolic multiplication and a sine hyperbolic term in z, and of course, the parabolic cylinder. So, we have about 6 of these, at least 4 of these expressions. For 4 of these cases, we will see the example in the next slide. Let us start with the hyperboloid, the example which is the expressions which are given here. Let us look at how the hyperboloid looks like. Well, that is an example of an hyperboloid. It is a wireframe diagram shaded with a color to give you not the effect of intensity illumination like Phong and Gouraud, all right, but this color indicates the direction. Okay. So, you have 3 axes x, y and z, and that is how the hyperboloid will look like in terms of the wireframe diagram. Okay. We will provide a sketch of this hyperboloid, which will actually look something like this. I think it is easy for you to visualize this sketch as well, where there are certain planes provided at the origin on the top and along the x y plane, we have along the x z plane as well, and this is the sketch from the wireframe diagram given here. Okay. And the expression of the hyperboloid was given in the previous slide as on the left bottom corner. Okay. So, that is the hyperboloid for you, the wireframe and the sketch diagram. We will go ahead and see other shapes, very interesting. Parabolic cylinder, this is easy for you to visualize. The parabolic cylinder, cylinder with a circular arc would have been a normal cylinder, since the arc is parabolic now, and it is called a parabolic cylinder. We had expressions of these earlier as well. Elliptical paraboloid, that is very interesting, looks like a bowl. The elliptical paraboloid expressions were given in the previous slide. Okay. And then we have the most interesting, the hyperbolic paraboloid. Hyperbolic paraboloid, the sketch of that is given here. Okay. And I request you to use a computer simulation toolbox in computer graphics to generate these surfaces, or use your own C++ OpenGL concepts and draw these figures and create a wireframe. So, these are the examples of quadratic surfaces: hyperboloid, parabolic cylinder, elliptical paraboloid and hyperbolic paraboloid as well. We will move on to Bezier surfaces, which are extensions of Bezier curves. The degree of the surface in each parametric direction is 1 less than the number of defining polygon vertices in that direction. Now, these Bezier surfaces are extension of Bezier curves. We talked of cubic splines, Bezier curves, we talked of quadratic surfaces. Now, we move to Bezier surfaces. As for a generalized conic, we moved on to a generic surface parametric form or non-parametric form, implicit representation. So, for Bezier surfaces also the same could hold good, where instead of a single curve, I will have a set of Bezier curves embedded like in a wireframe, a mesh form, which will try to represent a surface, and that is what we call a Bezier surface. And conditions which we talked about for a Bezier curve, most of them hold good for a Bezier surface, which, so we are going to talk about that right now. So, we talk of a polygonal net instead of a simple polygon in 2D for a Bezier curve. Now, we have polygonal net distributed in 3D, assume it to be a wireframe net distributing, and you are putting a surface on that. Okay. So, that is the net. So, the degree of the surface in each parametric direction is 1 less than the number of defining polygon vertices in that direction. This is the same as for the curve, where we had the number of vertices only for a polygon. In fact, there are 2 or 3 directions now for the surface, and the surface generally follows the shape of the defining polygon net. So, we have a polygon net, we will see how that is defined. Continuity of the surface in each parametric direction is 2 less than the number of the defining polygon net, and only the corner points of the defining polygon net and the surface are coincident, and the surface is contained of course within the convex hull of the defining polygon, and the surface is of course invariant under any affine transformation. So, if you look back into these points about conditions of Bezier surfaces, they are almost similar to the conditions which we discussed in the last class about Bezier curves. We talked about 2D polygon, the starting point, finishing point, the curve must be within the polygon hull. The tangents at the starting and ending point must follow the nature of the polygon at the edges of the polygon at the starting and the finishing point. So, all those conditions, the order must be 1 less than the number of vertices. So, the surface is an extension of all those curves. Okay. So, if you look back, I read it out again. The degree of the surface in each parametric direction is 1 less than the number of defining polygon vertices in that direction. Surface generally follows the shape of the defining polygon net. Continuity of the surface in each parametric direction is 2 less than the number of the defining polygon net. Only the corner parts of the defining polygon net and the surface are coincident. The surface is contained within the convex hull of the defining polygon, and it is invariant under any affine transformation. Okay. So, that is the equation of the parametric Bezier surface. So, now you see there are 2 parameters u and w instead of t, u and w instead of t, that is what you have, and these are the control points Pij's, and j and I of u, this is known to you earlier. We had seen, and let us look at the expression of j and I of u, it is exactly the same of what we did for a parametric Bezier curve, the Kmj also follows the same rule. Kmj of W follows the same expression, u replaced by W, n replaced by m, I replaced by J. So, the nature of these two expressions are same. We have two parameters u and W instead of t in the case of a Bezier curve. So, what about Bezier surfaces? How does it look like? This is an example of a polygonal net. You have P 0 0 P, so it is like a matrix, okay? P 0 0 to P m cross n, m is equal to n, in this case it is a square mesh, and we want to fit instead of a single polygon in 2D or 3D, if you could have fit a curve through this. Now, we have the whole mesh and we want to fit a surface on the 3D domain. Okay. So, this is what it could result. So, we can have a Bezier curve along all of these at the end, and the surface should start from these Bezier curves and end of the other Bezier curve, and it should also, it may not pass through all these points, but it should have the other properties. And this is, so if you see here the q u w, which is given by this expression, j indices running from 0 to n and m can be represented by this expression, where if you look at this expression within the bracket, that is a Bezier curve for any value of I. So, if any value of I running from 0, 1, 2 or 3 or from 0 to n, that is a Bezier curve for any particular value of I. Interesting. Okay. And similarly, the outside expression, if this is assumed to be a constant, the outside expression also is a Bezier curve. So, it is basically a combination of Bezier curves in 2 dimensions. You have a sequence of Bezier curves, say along x, and a sequence of Bezier curves along y. They are all interpolated and combined together to yield you a Bezier surface. So, you have a Bezier curve at the starting and the finishing point of this lines of the surface, ends of the surface. This is not end points of the curve. Okay, ends of surface will be lines or curves. So, in one direction you have, which is x, let us say in the xy plane, which is controlled by the parameter u. In the other direction you have w, which is controlling the other direction. So, that is what you have for a Bezier surface. If you look back, there are, you can have actually Bezier curves at starting and finishing points, and along each dimension, u and w, being talking about these 2 directions, the parameters. The Bezier surface in matrix form can be written as this, where you talk about the t's in the case of a curve. So, you have u's, you have w's, and this is the matrix B. This is the matrix B, which is the set of coordinate points which define where the surface should lie, define the geometry. And what about m and w? Well, u and w are defined here already, u and w are defined. This is the parametric row vector and the column matrix. B is the one. So, we look at n and m. What are n and m? That depends upon the degree of the curve you are fitting. So, if you have a 4 cross 4 bicubic Bezier surface in matrix form, this is what you will get. You look back into the expression of QUV, you have u, n, b, m transpose and w. Well, u and w are given. This is u and this is your w. Good. We talked about this earlier, depending upon the order. Then you have n, b and m. When you talk of n, b and m, this is your n, this is your B matrix and this is your m. If you see these two, the n and m are same, n and m are same, and they look like what? Can you guess? You have seen this matrix earlier. This n and m matrix, one is the transpose, of course, the other one, since it is symmetric, it does not matter much in this particular case. You have seen this matrix when we talked about the matrix representation of the cubic Bezier curve. Cubic Bezier curve had this matrix, which we defined with those coefficients lambda ij at the beginning of the class today, lambda ij's for the n cross n matrix. So, that is the matrix here which you have, the bicubic, because there are 2 of those, and these are your Bij's, the 4 cross 4 points in space which define the polygon net. You have the 4 control points, 4 cross 4, 16 of them, which define the polygonal net, okay, and those are put into the matrix. So, if you want to fit a 4 cross 4 bicubic Bezier surface using a matrix equation, you need this cubic matrix form from the Bezier curve. You need these elements up to the order in which you want to, since it is bicubic, it is cubic nature, and you just put these 16 elements in this particular form. It may not always be the case that you need to fit a bicubic curve only over 4 cross 4 points in space, only over 4 cross. You may be given, let us say, you may be given, let us say, 5 cross 3, a matrix of 5 cross 3 points instead of 4 cross 4, or it could be 4 cross 5. So, what do? You may need to fit a bicubic Bezier surface, because that dictates the order of the surface, that dictates the order of the surface, and you may need to fit our control points given by the geometry condition, which could be 4 cross 4, 16 as we have seen earlier, or it could be even 3 cross 5 or 5 cross 3. So, what happens if it is 5 cross 3? Let us take a case when we talk about non-square 4 cross 4 bicubic Bezier surface in matrix form. We talk of a non-square 4 cross 4 bicubic Bezier surface in matrix form, and we will look, since it is you see, this is the 5 cross 3, okay, non-square matrix is what you are using, and the matrix M cross N are no longer the same, they are not symmetric, they are not the symmetric of each other. This is the matrix which you had obtained earlier for the case of the 4th degree Bezier curve, J40, J41 up to J44, 4th degree Bezier curve. When we talked of this matrix, this is the matrix form, and the other one should be the quadratic one. So, based on this based on the number of points given, or the control points over which you have to fit the surface, you have to decide on the order of the elements in terms of in the direction u and w. The parameters u and w will point to two different directions of the surface, let us x and y in this case. So, u and w, you will find that if there are 5 points along a particular direction, you can choose up to 4th order. If there are 3 points minimum, you need 3 points, then you can choose a 2nd order, and hence those matrices M and N which we discussed earlier will be dictated by the geometrical conditions of this polygon net. The geometrical conditions of this polygon net is going to dictate which two matrices, that M and N in the formulation. If you look back into this expression here, you already have what is u and w. B matrix is defined by the geometry of the control points of the polygonal net. These N and M are the matrices dictated by the order of the Bezier surface which you are going to fit. Order of the Bezier surface which you are going to fit is going to dictate the size of the matrix M and N in that expression. So, if you see here this M and N which we talked about, the bicubic 4 cross 4 or 5 cross 3, depending upon the direction u and v, it will all be dependent on B. So, if you roll forward, you will see that for a 4 cross 4 bicubic Bezier surface in matrix form, 16 points are given. This is the matrix M and N. Whereas, if you have a non-square polygonal mesh to be fitted, and that is non-square 5 cross 3, but you want to still fit a 4 cross 4 bicubic Bezier surface, okay, then you on one side you may have up to the order 4, the other side you may have the order 2. It all depends on the polygonal mesh available. The number of control points available in each direction is going to dictate what is going to be your degree of the order M and N. I leave it as an exercise for you earlier in this class to check up the equations or obtain the equations for J2i and J4i. So, that will help you to obtain these matrices M and N which is given in this slide here. Please follow all the home assignments given and work out all the expressions which we have done in the last 2 classes, specifically the last class today, and that will help you to master these equations in practice. And before you go to the programming environment, as using any simulation toolbox or write a program using a high level programming language like C++ with OpenGL or FIGS as your standards in an environment, you should master these analytical expressions yourself, try to draw these curves, then simulate and see how these curves come out when you try to plot them, either to simulate a curve or to fit a surface or to obtain a curve for a trajectory in animation or to fit an experimental data in 2D or 3D, you are using these cubic splines, Bezier curves, Bezier surfaces, or even B splines. The other types of curves and surfaces which we have not talked about due to the time limitations available to us, but if we are able to master this, you will be able to learn about any other types of surfaces in terms of B spline surfaces or cones. There are other types of other surfaces which are talked about in literature and used by experimental people, computer graphics scientists and engineers to fit various plots in 2D and 3D, or to come up with representations to represent a solid, or to obtain a trajectory in a curve in 3D. Okay. So, I would request you to please kindly go ahead with the derivations and obtain all the different forms of matrices we have studied so far, also the different parametric expressions, look into the blending functions where 2 or 3 different curves are meshed together to obtain from one to another, and of course, the interesting geometric recursive definition of the Bezier curve. So, that brings us to the end of the lectures on curves and surface representation in today's lecture, and in the last 3 lectures we have seen different types of representations of curves and surfaces, and I would request you to kindly see them again, write them again, try to derive them again, run through the mathematics without any help if possible, to obtain a control over this representation. Thank you very much.